Hello students, welcome to this video. In this video, I'm going to explain the intensity of radiation and the relationship between intensity of radiation and emissive power of a black body. So we will discuss in detail. Before going to see what is intensity of radiation, we will discuss about a solid angle, and then we will study in detail about intensity of radiation. Intensity of radiation or radiation intensity. The radiation emitted from a surface which propagates in all possible directions. Similarly, the radiation incident on a surface may come from different directions. So in both cases, the effect of radiation on the surface depends on the directional distribution. Such directional effect, which may be treated by introducing a concept like intensity of radiation. So it is denoted as I. Okay, so this intensity of radiation is defined as the rate of a heat radiation in a given direction from a surface per unit solid angle per unit of projection of the surface on a plane normal to the direction of rotation. I will repeat once again. Intensity of radiation is defined as the rate of heat radiation in a given direction from a surface per unit solid angle per unit area of projection of the surface on a plane normal to the direction of radiation. So it is the radiant energy emitted by a black body at a temperature T streaming through a unit area normal to the direction of propagation propagation per unit wavelength about a wavelength per unit solid angle about the direction of propagation of beam. So it is denoted by IB lambda and can be expressed as IB lambda is equal to energy emitted divided by projected area into wavelength into solid angle, that is watt per meter square per steradian. Now we will see what exactly the solid angle means. A solid angle is defined as the ratio of area of spherical surface enclosed by a conical surface with the vertex of the cone at the center of the sphere to the square of radius of the sphere. A solid angle is defined as the ratio of the spherical surface enclosed by a cone with its vertex at the center of the sphere to the square of the radius of the sphere. So consider the emission from the differential area dA1 towards the normal area dAn. Okay, normal surface area dAn, or to say dA, through which the emission passes, or normal surface dA, which is shown in figure. The differential area dA through which the emission passes subtends an angle called the solid angle. So here you can able to see d omega, solid angle, and it is viewed when from this dA1. Okay, so mathematically it is expressed as d omega is equal to dA by r square or dan by r square, where a is the normal area and r is the sphere radius of sphere. Okay, so unit of solid angle is steradian, and solid angle subtended by a hemisphere from its center is always d omega is equal to 2 pi r square by r square, which is equal to 2 pi, and the solid angle subtended by sphere from its center is 4 pi r square by r square, which is equal to 4 pi. Okay, this we should remember. Now we will study the relation between intensity of radiation I and emission power of a black body. So this is a sketch, so you can able to see there. It is the radiation emitted by black body at temperature T over all wavelength per unit projected area per unit solid angle. That is intensity of radiation IB. Okay, so let us consider radiation from the elemental area dA1 at the center of the sphere. So you can able to see this is the elemental area dA1. Okay, so we will consider radiation from this elemental area dA1 to the center of the sphere, and the radiation absorbed by a second elemental area dA2, second elemental area dA2, this area, a portion of the hemisphere which is in which is at a portion of the hemispherical surface. Okay, and the projected area of dA1 on a plane to the line joining dA1 is and dA2 is equal to dA1 cos theta, dA1 cos theta. The solid angle is subtended by this second area, that's the second elemental area dA2, is dA2 by r square. Therefore intensity of radiation we can write I is equal to dq1 to 2 divided by dA1 cos theta into dA2 by r square. Call this as equation number 1, where dq1 to 2 is the rate of heat radiation from dA1 to dA2. Okay, so the projected area on a plane normal to the line joining dA1 and dA2 is a dA1 cos theta that we have already shown, and spectral intensity of radiation according to the definition we just wrote I is equal to dq divided by dA1 cos theta dA2 by r square. Okay, so rearranging this equation we can write dA2 is equal to r into d theta into r sin theta d phi, which is equal to r square sin theta d theta d phi. Call this as equation number 2. Now from equation 1 and 2 we get dq1 to 2 is equal to I into dA1 sin theta cos theta into d theta d phi. Okay, call this as equation number 3. Therefore the total radiation through hemisphere we can integrate this. So here we can integrate with respect to d theta as well as d phi. Therefore q is equal to integration of theta is equal to 0 to theta is equal to 5 by 2, and phi is equal to 0 to phi is equal to 2 pi. So double integration of I dA1 sin theta cos theta d theta d phi. So I and dA1 is common term, sorry, constants, so we can take it outside. So double integration of theta equal to 0 to theta is equal to 5 by 2 to phi is equal to 0, phi is, to phi is equal to 2 pi sin theta cos theta d theta d phi. So we will get phi d phi is equal to phi, so we will get to 2 pi into IdA1 into integration of theta is equal to 0 to theta is equal to 5 by 2 sin theta cos theta into d theta. So equating that, simplifying further, we know sin theta into cos theta is equal to sin 2 theta by 2. Okay, so theta is equal to 0 to theta is equal to 5 by 2, the integration boundary condition. So simplifying, now we know that sin 2 theta by 2 is equal to, sorry, sin 2 theta is equal to, this 2 is gets outside, so sin 2 theta d theta, so 2 get cancelled, 5 into I into dA1 theta is equal to 0 to theta is equal to 5 by 2 sin 2 theta d theta. Simplifying, we will get q is equal to 5 I dA1. So the total radiation through the hemisphere is equal to q is equal to EB into dA1. So this is equation number 5. So from equation number 4 and 5, I pi into I dA1 is equal to EB dA1. dA1 get cancelled. So EB is equal to pi into I. Thus, we can say the total emissive power of a black body is equal to pi times of the intensity of radiation. Total emissive power of a black body, which is a diffuse black body surface, is equal to 5 times the intensity of radiation. So this is a relation between intensity of radiation and emissive power of a black body. Okay, so I hope you understood this.